Hello, and welcome to Hopkins at Home. I am Noor Rawafi from the Johns Hopkins Applied Physics Lab, and I am the project scientist of the Parker Solar Probe mission. I'm going to cover a little bit of history of the Parker mission, and most importantly, the discoveries that are changing the landscape of the inner heliosphere. Let me first start with the far history of the solar physics research and the corona in particular. Humans are naturally fascinated by beauty, complexity, and mystery. And this is what led people to, to study, track, and document solar eclipses, as shown by these drawings on stones, by this scripture also on stones, but also other drawings and photography. And they did an amazing job. Look at this stone carving and modern photography of a solar eclipse. There is quite a bit of similarities. Now, solar eclipses did not only fascinate people, but they led also to big discoveries. And really, when I say big, they are major discoveries. Back in 1869, two American astronomers discovered independently a very mysterious emission in the solar corona. This is what we now know as the green line of iron 13. The mystery back then that nobody knew what was the chemical element that was responsible for this emission, and that mystery lasted 70 years. Only in the late 30s that a European spectroscopist made laboratory experiments and actually discovered that that emission was from iron ionized 12 times. If you translate this into other terms, the existence of this highly ionized heavy ions in the corona means that the solar corona is extremely hot. And the problem there is that the solar surface is much cooler. The solar surface is at about 6,000 degrees, but the corona is more than a million degrees. And that is actually what became known as the coronal heating problem. Since then, and 70 years later, we are still struggling trying to understand that phenomenon. And ironically, that from the discovery of the green line to the discovery of the coral heating, it took about 70 plus years. And from the discovery of the coral heating until now, where we launched Parker Solar Probe, Solar Orbiter, and other space missions, it's also 70 plus years. So the question is, what is going to come next? In other terms, what is the big phenomenon that we are going to discover, particularly with missions like Parker Solar Probe? Now, let me come back to the solar corona. The solar corona, as I said earlier, it is beautiful, fascinating, and mysterious. And as you can see from this movie from the Solar Dynamic Observatory, it has a myriad of structures, and it is all constantly changing. Even when the sun is extremely quiet, as you can see from the solar eclipse on the left-hand side, the corona is very complex. And it's also very dynamic, as shown by the right-hand side movie. That complexity and dynamics are synonymous, are a testimony of the very complex and challenging physical phenomenon that are taking place in that region of space. Now, why should be interested in studying and understanding how the solar corona works? The very simple reason is shown by this movie, illustrated by this movie here from the LASCO on SOHO, is that we live in the extended atmosphere of the sun. And whatever is happening in the solar corona can affect us in one way or another. And in many cases, it can affect us adversely. This is a great example. In 1989, there was a Carrington-like event that erupted in the sun and that caused um, a, a huge geomagnetic storm which caused also a power outage in the northeast of America. Imagine that we have one of these huge events that erupts on the sun and is hurtling toward us here on Earth, and it causes power outage across the globe. The economic system is likely to collapse. And if that happens, the likelihood of civil unrest is pretty high. And if, God forbid, that happens, its impact on our society and all the advances we made will be huge as well. In, in 2012, there was an event that missed Earth by a week. Had it happened a week earlier, it would hit Earth head on. And the damage estimate from that event, if it had hit Earth, it's over $2 trillion. That's really huge. That is exactly the reason why we are interested in understanding how the solar corona works, and most importantly, if we can predict and forecast these events, these explosions that are occurring there. So, and these explosions are not the only phenomena that we are interested in, but there are at least and three that are three phenomena that were discovered decades ago. They are historical and they are extremely challenging. The first one I already talked about, that's the coronal heating. As I mentioned earlier, the temperature of the solar surface, that is the photosphere that we can see with naked eye from Earth, is at about 6,000 degrees. You go a couple of thousand kilometers above, and the temperature of the plasma will jump to more than 1,000,000 degrees. And that is counterintuitive because from everyday experience here on Earth, if you have fire cam, the further you move away from that heat source, the cooler it gets. But obviously that does not hold for the solar corona. And we don't completely understand why that is. The other phenomenon is also closely related to the coronal heating is the solar wind acceleration. The solar wind is a flux of charged particles, that is electrons, protons, alphas, and heavy ions, that are constantly flowing away from the sun to fill the whole heliosphere. The issue there is that these particles, when you look at them very close to the base of the corona, they are almost standing still. But over a very short distance, they get accelerated to hundreds of kilometers per second. And there again, where they get that energy, we don't really know. The third phenomenon I already talked about, which is the uh, explosions on the sun, like flares and CMEs. They, when one of these big events erupts on the sun, usually they accelerate particles to almost the speed of light. And that's what we call them the solar energetic particles. And they are very hazardous to human exploration in space. They are hazardous to space equipment like the GPS satellites and communications. And they are also can be also harmful to us here on the ground, namely the power grid. Parker Solar Probe, the main science objectives of Parker Solar Probe is to address these three phenomena. But let me say this. Parker Solar Probe is an exploration mission in the first place. We are flying through a region of space that we never visited before. And that means whatever measurements we make there is a potential discovery. And that is exactly what we are seeing in the data. What we are seeing there are phenomena that we never even thought of before. They are completely new. Now, a bit of history. The history of the Parker Solar Probe idea is not really new. It dates back to 1958. It's over 60 years old, when the Simpson committees suggested three missions that NASA has to implement. The first of them, which is in C here, it's a probe that will orbit the poles of the sun, and that was implemented, and that mission is already over. That is Ulysses. The second mission is a solar probe that will orbit the sun within the orbit of Mercury, and that is Parker Solar Probe. The third mission is a spacecraft that will leave completely the solar system and basically have a look at the solar system from the outside. Hopefully that will happen in a few years from now. Since then, since 1958 until 2007, dozens and dozens of studies and attempts to implement this solar probe mission, but they didn't all come to fruition, simply because this mission is extremely challenging, and it is extremely hard to protect the spacecraft when it is very close to a star. The environment there is extremely harsh, and you need special material to protect that spacecraft. And that material was not available until 2008. Back then, when we at APL came up with an ingenious idea and inventions that allowed us to implement this mission. This is basically different historical concepts of the Parker mission that were all suggested to NASA, and they were all not acceptable because they were either extremely expensive and NASA cannot afford them, or they were not viable. But now, since 2018, Parker Solar Probe is real, and the rest is history. Now, what made a mission like Parker Solar Probe? Um, what made the Parker Solar a mission like Parker Solar Probe to come to existence? As I said before, we had really to make breakthrough invention in terms of technologies. We cannot have a Parker Solar Probe without having a heat shield that can protect the spacecraft, like this one here. This heat shield is made of carbon foam that is sandwiched between two layers of carbon composite. When we are flying very, very close to the sun, this side that is facing the sun will be glowing at over 2,500 degrees Fahrenheit. The back side of the TPS, the thermal protection system, is at about 700 degrees. And a meter behind that, we are at room temperature. And it's exactly there where most of our instrument reside. It's on the bus, this structure here, and they are operating at room temperature. There are a couple of exceptions there, which is this small instrument. This one, it's the Faraday cap, is an instrument that measures the solar wind, and these electric antennas, they are also exposed to the full solar environment. It is also for the first time that we fly solar panels that are water cooled. This never been done before in the space age. In terms of science instruments, they have to be the most sensitive and basically the state of the art. These are probably the best instruments ever flown in space to measure plasma, like the solar wind. Our flight system and payload, as I mentioned earlier, we have the TPS that is in front. We have the radiators that are their responsibilities to cool the solar panels, mainly that are water cooled, and we have the bus here that harbor all the instruments. And we have 4 instrument suites. Let me start with the very first one, which is the imager WSPR. It's this box here. And what WSPR looks to the side of the sun, and it images basically the young solar wind as it gets accelerated from very close to the sun all the way past Earth. We have the fields suite. It has 5 electric antennas. 4 of them are mounted behind the TPS, and it has also magnetometers that are mounted in the boom. And they measure electric fields, magnetic fields, fluctuations, densities, temperature, you name it. We have ESS, that is the energetic particle suite. It resides here. And we have the sweep instruments. It has 3 instruments, SPC, SPAN A+, and SPAN B. They all measure the thermal solar wind. Now, how this mission is going to be implemented and how we are going to this distance very close to the sun. Historically, people thought about flying the spacecraft all the way out to Jupiter and basically swing it back toward the sun. That's the only way people thought about having a spacecraft to get as close as possible to the sun. But in 2007, our APL's engineers, they came up with another idea that basically if we fly by Venus multiple times, we can achieve very similar result. And the advantage there, instead of having a mission that lasts for a couple of passes by the sun, we can have a mission that can last for years and years and years. And that's actually what we came to implement as Parker Solar Probe. But the ultimate goal is to get within 10 solar radii from the solar from this the sun of the center, and we will achieve that in 2024. Since the launch in 2018, we completed 7 orbits, and of these 20 of the 24 orbits that are the prime mission of the spacecraft. And so far, the spacecraft and the payload are doing a marvelous job. We do not have any issues, and everything is going really well. I believe I was ahead of myself, and I already talked about this. Okay, let me now go a little bit to science and what are the discoveries that we are making in the solar wind. Let me first say this: when we launched in 2018. It was a deep solar minimum. The sun was completely quiet. If you look at the sun at any day, it is completely spotless. And it's, to say the truth, it's a little bit boring for a solar physicist like myself. But it was probably the best time to launch a mission like Parker Solar Probe. And the reason for that is that the solar wind by nature is a very complex medium. And it's best to start with its simplest state, which happened to be during solar minimum. And as the solar maximum progresses toward the solar cycle activity progresses to the maximum, we will get that complexity progressively. So from 2018, we are now here. This should be 2021. The sun started waking up. We are getting signs of more and more activity, but the end of the Pride mission will coincide with the solar maximum, and we would have covered a half solar cycle. And if everything goes well, we can go to other solar minimum, and that will be the goal of the objective for the extended mission. Let me go to the first big discovery that Parker Solar Probe made. It's the dust-free zone. Back in 1929, 90 years ago, a physicist named Henry Russell made a prediction that there should be a region around the sun that is completely devoid of dust. The existence of dust particles uh, is there all the time in the heliosphere, but his thought is based on the fact that when you are very close to the sun, the dust particles get heated to extreme temperature to the point they basically evaporate, and they also ionize. And once that happens, they get cleaned out by the radiation pressure, but also by the solar wind. And that's why we should have this dust-free zone around the sun. But since then, people looked for it over and over and over again, but there was no evidence for it whatsoever. Back last in 2019, December of 2019, Parker Solar Probe gave us the very first evidence for the existence of this dust-free zone. This is basically an image for uh, the light scattered by dust around the sun. And if we plot the intensity of that light along the photometric axis, which is the axis of symmetry of this emission, and you plot it as a function of elongation or distance, what you see from Earth is this dashed line and these the dots here. And you can see it's increasing all the way to the sun. It does not decrease, meaning that there is no dust-free zone. But what Parker Solar Probe saw when we are closer to the sun, actually that intensity starts declining. And that was the very first evidence that the dust density is also closer to the sun is getting down. And that is the first hint about the dust-free zone. So that result were obtained at the very first perihelion, which was at 36 solar radii. Once we got closer to the sun at 27 solar radii, that decline in the F corona intensity actually got bigger. And actually what sealed it off, the dust-free zone is there, and that was the evidence for it. So this discovery is historical, and it's big, and it tells us something about the dynamics of the dust close to a star. And this potentially can have implications on studies of other stellar systems that are not necessarily ours. Other Very interesting observations are about CMEs, coronal mass ejections. We have seen tons of them from 1AU. And the problem with observation of 1AU, you do not have much insight into the internal structure of that cloud. But with Parker Solar Probe observing them from close by, that's actually um, very thing that we are learning, that is new, that we are learning. We are having access to very fine details that are telling us a lot about the internal structure of CMEs, and that's actually will help us improve our models, and potentially they will also help us improve our forecast of these events. But this is not the only thing. When we don't have CMEs, we are observing that the solar wind is not quiescent as we see it from an AU. It's extremely dynamic, and it's always impregnated with very small structures that are like very small flux ropes that are erupting all the time, and they are leaving the sun all the time. That is something really new that we have not seen before. Another very interesting observation is, let me say this before. When we launched Parker Solar Probe, as I said before, it was during a solar minimum. And whenever you look at the background of energetic particles, you don't see much. You only see energetic particles from uh, CARs, co-rotating interaction regions. But the sun itself doesn't seem to produce much of them because simply it's very quiet. But when Parker Solar Probe flew very close to the sun, that actually changed. What we've seen then is a myriad of very small energetic particle events. The source of many of these energetic particle events is not well known. We know that events like this one, it's a CERs, and we know them, but these small events, we don't know them. But why they are so important to us? There is theories out there about what we call the seed particles. The seed particles, they are population of particles that are energized to a median level of energy to 1 MeV or something like that. And when big events come by, they just take this population and accelerate them to a fraction of the solar wind, and that's what makes the energetic particles. And people were arguing about the existence of the population for years and years and years, but nobody had any evidence how this population, whether this population exists, and whether how it is created. We now think that these small events might be actually the source of this seed particles. And if it is the case, then that's really a huge discovery, because we now understand what. First of all, we know what the sun is doing when even when it is very quiet, it is still producing particles. But the most important thing that we know where those how energetic particles get accelerated to the speed of light. A good example of these small events are a series of events. We see six of them here. There is 1, 2, 3, 4, and 5, and 6. But what is also fascinating about them, they don't they are not all similar. They have differences. If you take this triplet, 3, 4, and 5, they actually occurred within 48 hours. They were separated by less than 24 hours from one to the next. The abundance of event 4 is completely different from that of event 3 and 5. And the thing is that we think that they are all coming from this region here. You can see it's erupting uh, over and over again. We think they are coming from that same active region. But if they are coming from that active region, why should they have a different abundance composition? And that is actually mysterious. We do not really understand why. And also, as I said, although these events are very small, they are prominent, and they are actually leading us to new insights and led us to new questions that we have to answer about them, and potentially about the big events as well. But let me say this. The the good news is that the sun is waking up again, and we got the most powerful CME and the most powerful flare in 3 years, on the last 3 years. That is an M class flare that erupted on November 29th. That was on the East Limb here. And with it came the fastest CME in the last 3 years. It's almost a 1,400-kilometer CME. And the nice thing is that event erupted on the East Limb as seen from Earth. That is about here. Look where Parker Solar Probe is located. It is just facing it. And that CME just flew past by Parker Solar Probe as shown by this simulation from the CCMC team at Goddard. That CME flew past Parker Solar Probe on June 1st, and we got a ton of data from it. All our in situ instruments were on and collecting data, and that data is being analyzed, and there is some papers that are being written about it. Let me go now to another big phenomenon that it is one of the major discoveries of Parker Solar Probe. It's what we call the switchbacks or magnetic field reversals. From all previous missions that flew far away from the sun, we are used to fluctuation in plasmas. And in plasmas, it's normal to see fluctuations. It's not really a surprise at all. The only thing is that these fluctuations are low amplitude fluctuations. They are small. And what we are looking here, by the way, is the magnetic field. This region here is the region that Parker Solar Probe is giving insight of for the first time. Look at the amplitude of this fluctuation. It is huge. And just let me tell you a little story about it. We got this first data set back in December of 2019. That is 2 days before the AGU. And we were looking at this data almost live as it's coming down. And we thought that there was something wrong with the instrument. It took us less than 10 minutes to figure out, no, the instrument is actually working right, and these structures are real. What we are looking at are reversal of the magnetic field. What you have is you have a field line that is going this way. It makes like an S shape and out again. That is, it flips over itself back to the sun and out again, and it does it over and over and over again. This structure that we call switchbacks, they are actually not the change of polarity. It's the same field line, and we can prove that from the strahl, the electron strahl. The electron strahl will just change direction, and also from the pitch angle of electrons that changes sign. So we are in the same field line. And by the way, they come in groups, and they are separated by periods of very quiet magnetic field. This period of quiet magnetic field, the field is almost radial, doing nothing. This movie is an animation, obviously. It basically illustrated what we were talking about. You have a field line that reverses of itself and goes back again. So, but what is fascinating about this? Let me address the energetic aspect of them first. First of all, they are highly galvanic. The correlation between the flow and the field is almost one. The thing, as I said before, they come in groups, and they are separated by this quiet period of the magnetic field. When you look at the energy budget of the Poynting flux or the kinetic energy of protons during the quiet period, those energies are low. But when the switchback come by, the energy budget shoots through the roof. What this tells us that this phenomenon is very energetic, and it's also turbulent. And this is exactly what we are looking for the last 60 years. We are looking for energy sources that potentially will hit and accelerate the plasma and the solar wind, which are the first and second goal of the Parker Solar Probe mission. The other thing that we can also, it's an open question, still an open question, it's about the nature of the solar wind. When you look at properties of the solar wind during a period that is dominated by the switchbacks and the quiet period, they are quite different. And there again, are there two sources of the solar wind? Is this like dominated by reconnection or turbulence? And this one is just evaporation from the base of the corona. These are still open questions. And by the way, the nature of the solar wind, whether it is intermittent or continuous flow, it's an open question for decade now. And probably Parker Solar Probe is giving us an insight into that. But the big thing about the Parker Solar, the switchbacks that are observed by Parker Solar Probe, they actually they probably will play the discriminator between the most prominent theories of the solar wind, that is magnetic field reconnection or versus turbulence. And if if we can solve this enigma, that's really huge discovery for us, and it's big step forward in our understanding of how the solar how the corona works. Let me just give you um, a few examples why people are so fascinated and interested in this phenomenon. Over the last 3 months, there were uh, four models that were published about this. Four models that were published about this phenomenon. That are these four papers here, and there was another paper that were published a little earlier about them. So over about 6 months or so, we have five models already about them. And I bet you there will be other models that will be coming. So again, these models are addressing different aspects of the switchbacks. Do they all solve everything about them? No. All of them have limitation here and there. They cannot reproduce everything we observe. And that's why the switchbacks phenomenon is really a big and challenging problem, and it can be actually the one of the biggest discovery made in the solar wind going forward. And who knows, it might last for years and years and years, like the coronal heating. Another very interesting observation that were made by Parker Solar Probe, and this time by the thermal solar wind suite, that is SWEEP. Um, from this cartoon, what we are used to, that the eniosphere can be divided in two regions. The region that is immediate to the sun, that is the solar corona, it is dominated by the magnetic field, and it basically rotated rigidly with the sun. But as we move out, that rigidity breaks down, and basically the solar wind will shoot radially outward, and that causes the magnetic field to curve backward, because the magnetic field keeps anchored is still anchored to the solar wind. As the sun rotates, make it curves backward. This is the issue with it. Over years and years, we thought that this transition between the inner region and the outer region occurs at about 10 to 15 solar radii. What we are learning from Parker Solar Probe, that actually that this rotation extended much further out. Um, Let me explain what we are seeing in this graphic here. This cyan curve here is the tangential flow as a function of distance given by the best model we have for the solar wind. And as you can see, it's very low. It's almost zero. The data points here is the tangential flows as measured by Parker Solar Probe. And as you can see it at 35 solar radii, we have probably something like 10 to 20 more tangential flows than what we are seeing. Let me say this here. We are revising this data, and probably we can cut this by a little bit, but still, the tangential flows measured by Parker Solar Probe are more significant than what is predicted uh, by the models. So the very first victims of an observation like this are the models we have for the solar wind, and for the we have to revise them without problem. But this has also a bigger side to it. It is giving us a new insight how a star like the sun loses angular momentum. So we thought over years and years by models like this that we have a good understanding how the sun was born rotating faster and slowed down as it's aged. but probably that is put in question by a measurement like this one. And if that materializes, we might actually have to revise also other models of the other stellar systems of different nature than the sun. And also, this might also have an implication on the formation of the whole solar system as a whole. Again, this phenomenon, we already have several papers trying to discuss it. I don't think we are we got hold of it. I think there is still a lot of things that we need to understand about it. So Parker Solar Probe is not only, I said earlier that Parker Solar Probe is doing really well. Pre-launch, we had the plan, and the plan is basically we turn on our instruments only when the spacecraft is very close to the sun. It's below a quarter of an AU to the sun, and that's what we call encounters. And that constraint is dictated by power and other limitations that we thought exist on our design of the spacecraft. But once we launched the spacecraft in Spain, we actually discovered something about it. It is behaving way better than we ever thought. So the first thing we did, the instruments are on almost throughout the orbit. They will be turned off only when we are downlinking data, and that's a very small duration of the whole orbit. So we are collecting way more data than we thought over a large range of distances. Um, the other thing also, we are downlinking 5 to 10 times more data than we thought, which is really good for a mission like Parker Solar Probe. Because if you think of it, we waited 60 years to get this mission, and looking down the road, we may not have a mission like it for the next 20, 30, 40 years. Who knows? Hopefully we'll get more, but it's not certainty. But an interesting thing that we kept doing is when we fly by Venus, we turn all our instruments on and try to study the induced magnetosphere around Venus, and we are making quite a bit of discoveries around there. I know that our prime objective is the solar wind and the corona, but still, uh, our instruments are really performant around Venus, and we have a special issue that will be coming out in GRL that will have between 7 to 10 papers. I believe 5 of them are already accepted, and we are still waiting for the rest to. The rest are still under review. This is an animation about the Venus flyby, the last Venus flyby. As you can see, it flew by Venus, and we have an eclipse as the spacecraft went behind the planet, and it emerged on the other side. Um, so far we did 3 of them in February 20th. In less than 3 weeks from now, we will do the fourth, and we have 3 more to do, and that will take us to 10 solar radii from the sun. In terms of publication and special issues, first of all, we had our very first results published in Nature in December of 2019. As you see by the cover here, we had 4 science papers. We have the editorial. We have basically everything we can have on Nature. We had also a piece by Eugene Parker, after whom the mission is named, published in Nature Astronomy on December of that same year. But since then, we have 3 special issues. Basically, in 1 year, we have 3 special issues. That is one in the Astrophysical Journal that has 59 articles. Another one in Astronomy and Astrophysics. It will have nearly 40 papers. And I mentioned the GRL about Venus. But our statistics, and we are not really performant. We are missing a lot of papers about the mission. But so far, we are counting between 250 and 300 papers on the first year alone. But as I said, we are missing other papers, and we are trying to catch everything about them. So this mission is producing a lot of science on its first year alone. Usually, when I give talks like this, I got asked a question: okay, what will happen for the spacecraft after the 7-year prime mission? If everything goes well, the hope is to continue orbiting the sun as far as we can. And in terms of propellant, we launched with 80 plus kilograms, as shown by this bar here. This is what we have remain, what we have on the spacecraft. It's about 70 kilograms. And for the whole 7 years of prime mission, we expect to consume about 8 kilograms, less than 10 kilograms. So by the end of the 7 years, we will still have something like 60 plus kilograms in the spacecraft. And as I said, if everything goes well, Parker Solar Probe can keep going for years and years and years to come. And I hope that we will do that. If we do it, it will be amazing for science. And I want to give a shout out to the Parker team and all the science team that are working out there using our data and producing science. This collection of photos is about how we are operating our mission during the COVID pandemic, and our team was proactive early enough to prevent any adverse impact of the COVID. And as a consequence, we are operating under nominal conditions without any impact on on Parker Solar Pro. So I will leave you with this movie, which is basically about to give credit of the people, some of the people who worked on the Parker mission, and it's also a little bit of memories to some of us how the mission came about and all the moments, critical moments that we went through. So please, if you have questions, I will be happy to answer them. And thank you very much for your attention. Okay, there are some questions already. Let me, from Elliot, can you use the data that you've collected with the probe to make predictions about the future behavior of the sun, such as future eruptions and their locations? Um, we can do it. We will contribute. We'll definitely contribute to that. One of the main objective of the Parker Solar Probe mission is to understand the microphysics that govern the corona and the solar wind. And if we get hold of that, we can basically get that knowledge and put it into models that deal with forecasting these eruptions. Yes, definitely we'll make advances on that. Whether the data itself that coming from Parker Solar Probe will allow us to make the prediction, the forecast itself, I would say no, but it will help us tremendously into understanding what goes on when these phenomenon are ejected from the sun and flying toward Earth. That definitely will help us doing that. Another questions for Marcy. Can you share more about the engineering behind the probe? How did you determine which material would survive this type of journey? That's an excellent question. Let me say this. As I mentioned earlier, that the idea of Parker of a solar probe is over 60 years old. And we had to wait all these 6 decades simply because we did not have the technology to implement this mission. We did not have the right material, or the mission was, astronomically expensive for NASA to afford. Back in 2001, NASA commissioned APL to look into materials, light materials that can be used to as a for a heat shield for a mission like Parker Solar Probe. And that took us 5 to 6 years. And you see it in the movie, by the way, here, to come up with this material here that is the uh, carbon 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 composite foam that we used for the heat shield. Once we realized that we have that material and it's performant, we did all sorts of tests about them. Um, and we knew that that's actually probably the right material. NASA actually issued the AO for the mission, but without that success, technological success, we would not have a mission of like Parker Solar Probe. Um, let me say other things about. Usually, when we talk about Parker Solar Probe, we talk about the TPS, and that's without that piece, we cannot have the mission. But the if you look at the other subsystems, they are they are as important as the TPS because without them, the mission still cannot survive. Let me give you an example. The the guidance and control system that basically controls the altitude of the spacecraft. So when we are flying close to the sun, the TPS has to be facing the sun all the time. The spacecraft can wiggle here and there a little bit, but that jitter cannot exceed 1 degree. And 1 degree is really, really tiny. And how we control the spacecraft? We have other subsystem. We have thrusters, we have momentum wheels, we have solar limb sensors, we have um, star trackers, and all together work with the TPS to keep the spacecraft pointed at the sun. Same thing for the solar panels I mentioned earlier. Um, Solar panels, they are water cooled, but also they are dynamic. When we are far away of the sun, we deploy them completely. But when we are closer to the sun, we actually stow them back closer to the spacecraft, and we leave only the tips of them illuminated because that's enough to give us um, the power we need for the mission. Another thing that is also important for Parker Solar Probe. Parker Solar Probe, when it goes closer to the sun, it gets very hot. When it goes further away, it cools down. So having material that survives this cycle of heat and cooling down, it is not evident. But so far, everything is working well. Another question from Jane. Does the behavior of the solar wind provide any parallels or characteristics through which we can identify other solar system or planets that might sustain life? Let me say this. First of all, the solar model is basically the base for other for stellar models. Obviously, you have to adapt for different types of stars, but still, our solar model is the first laboratory that we have to go to when we are studying other stellar system. Definitely, yeah, understanding the solar wind, how it behaves, will help us tremendously in constraining models and also probably future observation of other stellar systems. I mentioned the image of the six planets. As I said, when we looked at it, we as Parker Solar Probe, as heliophysicists, honestly, we thought, yeah, it's a nice image, but that's basically it. Is there much science in it? The planets are saturated and all that. But our colleagues doing exoplanets, they were so excited about it. And actually, we had a meeting with them a few days ago, and we talked probably we will have custom observations for them with very low exposure times. That way, the planets will not be saturated, and that will help them probably derive some characteristics about exoplanets and also optimize their models. So our observations can be used for other science that is not necessarily the prime science for Parker Solar Probe. Um, from that, the fourth question is from Dr. Fishbein. Have the particles streaming from the sun interfered with in any way with your communication with the spacecraft? How do you communicate when the probe is behind Venus and the sun? That's a very good question. So our communication, there are different ways of communicating with the spacecraft. Um, Let me start with there are periods when we have complete blackout. We cannot communicate with probe, and probe during those periods, actually when we are in the encounter mode, it has to be 100% autonomous. That is, if something happened to it, the spacecraft have to solve it by itself. We cannot do anything for it. When we are very close to the sun, there is one mode uh, that we of communication between ground and the spacecraft. That is what we call beacon tones. And beacon tones are very limited bits of telemetry, and it tells us the overall status of the spacecraft, whether it is at operation mode level 3 or 2 or 1. So far, when we are doing encounter, the spacecraft was always at level 3, which is the optimal. A few times when we were further out, it demoted to level 2 for a reason or another, but they were not severe at all. We corrected for them, and that was fine. Um, uh, we never got to level 1, which is great. So in terms of downlinking the data, it is very geometry dependent. We have to have a very clear sight between the antennas of probe and Earth. We can um, we can change the altitude of the spacecraft a little bit here and there, but there are constraints there. So our downlink is really constrained by where the spacecraft is in the space and with respect to Earth and the Sun. But when there is the angle between the Sun and Earth is small, then we cannot do anything about it. Um, yeah, when we are around Venus, usually, yeah, we can track the spacecraft pretty well. Our engineers, they need it for Doppler and other data to optimize the orbit and to plan future TCMs, which is the trajectory correction maneuvers. That way we can communicate with the spacecraft around Venus, or for that matter, basically elsewhere outside of the encounters. So, okay, there are no more questions. I would like to thank you again, and I hope you enjoyed this presentation about the Parker mission. And please, if you are interested in any aspect of this mission, the data or any other aspect, please do not hesitate to get in touch with us, and hopefully we get other opportunities to talk to you about it. Thank you very much, and have a good day.